Okay, on this example, we have a related rates problem. So we're going to read through this, try to label things as we go, and walk you through step by step. We're trying to find the rate of change that the area of this triangle is changing. So we have a 10-foot long ladder that's leaning against a building. All right, so I'm going to go ahead and label this side as 10 feet, all right, because that's where our ladder is going to be. And we're told that the base of this ladder is being pulled away from the wall at a rate of 3 feet per second. So pulled away from the wall at 3 feet per second. We'll label that in a second. Determine the rate of change of the area of the triangle. All right, so we want to figure out, in the end, we want to figure out how that area is changing with respect to time. So that's our big unknown for this problem. The other information that we're given in this case is we are also told we want to know exactly how this area is changing when the ladder is 6 feet away from the wall. Okay, so getting all these labels in here, what I like to do is I like to say X is the horizontal component, Y is the vertical component on ours, and that information that's given to us, they're telling us the rate at which this ladder is being pulled away from the building. So that's the horizontal change, right? How our X is changing with respect to time, it's 3 feet per second. Just labeling things as we go. So our X is increasing, so it's going to be a positive 3 feet per second. If that was getting pushed somehow in towards the wall, then it would be a negative because our horizontal distance is getting smaller. Okay, some other things we want to fill in here. We're told that the horizontal distance that the ladder is away from the building is 6 feet. So I'm going to go with an X value of 6 feet as we're looking at this. Some other things we'd like to kind of outline here. Our area formula for a triangle is just going to be 1/2 base times height. So in our case, I've written this as X as our base times the height along the wall is going to be Y. So we're going to have to differentiate that with respect to T in just a second. The other equation that always comes in handy when we're dealing with right triangles tends to be the Pythagorean Theorem, where we're thinking X squared, kind of along the bottom, plus Y squared along the side is equal to our hypotenuse squared. So in our case, our hypotenuse is 10. It's going to get squared. All right, so that formula is going to come in really handy for a couple different things. I'll show you in just a second. But before we get there, let's go ahead and differentiate our area formula with respect to time. So on the left-hand side, we can get a dA dt. All right, differentiating A with respect to T. On the right-hand side, though, what I'm going to do is we have two variables hanging out over here. So I'm going to treat those as two functions. I'm going to bring the 1/2 is going to come along as we take this derivative. But then I need to use the product formula to differentiate X multiplied by Y. And we want to be a little bit careful as we go through this. I'm going to lay it out. The product formula for taking derivatives is going to be the derivative of F multiplied by the second function, G is what I'm calling Y, plus leave the first function alone, multiplied by the derivative of the second function. So that's just kind of the map for how we're going to use this product rule. So the first thing is, let's take the derivative of X, our F function. So the derivative there would just be a 1, but because our variable was X, we need to include a dx dt with this. And then that gets multiplied by our G function, which I'm just calling Y. And then we copy down F, which in our case is that X, multiplied by the derivative of G. Well, the derivative of Y, our G function in this case, is going to be 1, but we also need to include a dy dt because our variable there was Y. We're taking the derivative of that with respect to time. All right, so now that all of that's laid out, what information can we fill in? Now it's still going to be dA dt on the left-hand side. That's just going to kind of come along. I'm going to drop the 1 because it's multiplied by some other stuff. What else can we fill in though? Well, we know dx dt is 3 feet per second, so we can fill in for that. We don't know what y is right now, so we're going to have to find that in a second. So I'm going to skip it for right now. Let's move on. We know x is 6 feet, right, from over on the left-hand side. I'm dropping the 1 again because we have other stuff multiplied by it, and we don't know what dy dt is yet. So we have to find those two pieces of information. We don't know our y value, and we don't know our dy dt. That's where that Pythagorean theorem is going to come in handy. Okay, the first place we can use it is we know a value for x, right? We know our x value is 6 feet. So we can plug that in for x here. Plus y squared is going to equal, that's 10 feet squared. So I'm going to go ahead and say 10 feet. Sorry, I should put that in parentheses squared. All right, that was given to us as it was a 10-foot long ladder for our hypotenuse. So this will be what, 36 square feet plus y squared is going to equal 100 square feet when we get done here. We want to isolate the y squared on one side, so I'm going to go ahead and subtract the 36 square feet from both sides. If you're okay with it, I'm not going to show that work. I'm just going to get 100 minus 36 gives us 64. In our case, the units are going to be in square feet for right now. And then to isolate the y and get rid of the square, we're going to apply a square root to both sides. This should give us y equals, well, the square root of 64 is 8, and the square root of feet squared is feet. So our y value here can be 8 feet, is how far up on the building this ladder is reaching when it's been pulled out 6 feet from the base of the building. So we can fill in right here, we can get 8 feet goes in for y, but we still need that dy over dt. So again, let's revisit that exact same formula. We had x squared plus y squared equals 10 feet squared. What we're going to do in this case is go ahead and differentiate this equation with respect to time, t. So to do that, we'll do one term at a time here. We get 2x. We also need to include a dx dt with this. Right, because our variable was x, we're differentiating with respect to time. And then y squared, its derivative goes dy. But again, need a dy dt with this. And on the right-hand side, you may note that's just a constant, right? If we multiplied it out, it would be 100. Derivative of a constant is always going to be 0. All right, let's see what can we fill in to each one of these spots. Well, the 2's here. Our x value, we could say that's 6 feet from our triangle, right? We know dx dt was 3 feet per second plus 2, and now we know our y value was 8 feet. We just did the work to find that. We don't know dy dt, but it's all equal to 0. Okay, so that's actually setting us up pretty nicely. We have an equation that has a bunch of numbers and a dy dt. So let's work on solving that down and getting dy dt on one side by itself. That shouldn't be too bad. So 2 times 6 times 3 works out to be, what, 36? And then feet times feet per second is going to be feet squared per second. Plus 2 times 8 is going to be 16. And we have feet. And then dy dt still hanging out over here. Next, I'm going to go ahead and subtract that 36 feet squared per second to the other side. So 16 feet multiplied by dy dt is equal to negative 36 feet squared per second. And to wrap this up, get dy dt on one side all by itself, we need to divide both sides by 16 feet. This will isolate the dy dt on the left-hand side as I've written it all by itself. And on the right-hand side, we should be able to simplify a little bit here. I believe this works out to be negative 9 over 4. All right, they're both multiples of 4. And our units are going to be feet over seconds. And why that is one of these feet in the numerator cancels out with this feet in the denominator. Okay, so back up to our formula. We're going to use this value, and it's going to go in for dy dt. So up here, -9 force feet per second gets filled in there for dy dt. Now it's just a matter of simplifying this down. Okay, so dA dt on the left-hand side is going to equal, let's simplify what we can, the 1/2 will come along. And then we have 3 times 8, it's going to make 24. Feet per second multiplied by feet is feet squared per second. Plus, let me think, we're going to think of this as over 1 for right now. So we have 6 times -9 up in our numerator is going to make a -54. And then 1 times 4 makes 4 in our denominator. Our units go feet times feet is feet squared per second. Let's go ahead and reduce a little bit. We still have dA dt on the left-hand side. The 1/2's coming along. I'm going to bring along our 24 feet squared per second. But then over here, that 54 and 4 have a common factor of 2, so we could reduce that to 27 over 2 feet squared per second. In which case, we want to kind of get a common denominator here. I'm going to visualize this as 24 over 1 and multiply both numerator and denominator by 2. That'll give us a denominator in common. So dA dt, just kind of bringing it along, is 1/2 multiplied by 48 over 2 feet squared per second minus 27 over 2 feet squared per second. So dA dt is 1/2 of, let me think, 48 minus 27, combining those numerators, is 21. Keep the common denominator, feet squared per second. And then multiply that 1/2 to the inside. We get 21 over 4 feet squared per second as our final answer for exactly how that area of this triangle is changing. It's increasing because that's a positive value at the time when we are 6 feet away from the building with the bottom of the ladder. So I hope this helps out as you're working through these. It takes a little bit of time and getting used to them. Keep practicing. It's really not the worst thing in the world. Just take your time. You got this.